Every extraordinary engineering achievement begins with an idea that many people believe is impossible. Standing on an empty piece of land, it's difficult to imagine that within a few years, this place could become one of the world's most impressive bridges, tunnels, airports, or skyscrapers. Yet every mega construction project starts exactly this way, with a vision, a challenge, and a team determined to turn imagination into reality. Unlike ordinary buildings, mega projects are designed to solve problems on a national or even global scale. They connect isolated regions, reduce travel times, strengthen economies, protect communities from natural disasters, and support millions of people every single day. Before a single excavator arrives, engineers spend months, sometimes years, studying every detail of the site. Teams of surveyors scan the landscape using drones equipped with LiDAR technology, creating highly accurate three-dimensional maps of the terrain. Satellites provide additional data, revealing how the environment changes over time. Geologists drill deep into the earth, extracting soil and rock samples from dozens of locations to understand exactly what lies beneath the surface. Every layer of soil tells a different story. Some locations contain solid bedrock, capable of supporting enormous structures with relatively shallow foundations. Others consist of soft clay, loose sand, or waterlogged ground that requires complex engineering solutions before construction can even begin. In coastal regions, engineers must also account for tides, erosion, and saltwater corrosion. Mountain projects introduce entirely different challenges, including unstable rock formations, landslides, and extreme weather conditions. Desert construction demands innovative methods to manage shifting sand, intense heat, and limited water supplies. No matter where a project is located, understanding the environment is the first and perhaps most important step towards success. At the same time, architects and structural engineers begin transforming concepts into detailed digital models. Using advanced building information modeling, or BIM software, every beam, column, pipe, cable, ventilation system, and maintenance corridor is designed inside a virtual environment before physical construction begins. This digital approach allows engineers to detect potential conflicts months before workers ever step onto the site. Instead of discovering that two systems occupy the same space during construction, software identifies the problem immediately, saving enormous amounts of time and money. As plans become more detailed, environmental specialists evaluate how the project will affect surrounding ecosystems. Rivers, forests, wildlife habitats, and nearby communities are carefully studied to minimize long-term environmental impact. Modern engineering is no longer measured only by speed or scale. It is also judged by sustainability. Reducing carbon emissions, recycling construction materials, protecting biodiversity, and improving energy efficiency have become essential goals for today's largest infrastructure projects. Once planning is complete, the construction site begins its dramatic transformation. Temporary roads are built to support heavy equipment. Massive fencing surrounds the area to protect both workers and the public. Portable offices, maintenance workshops, material storage yards, fuel stations, medical facilities, and quality control laboratories appear almost overnight. Soon, thousands of skilled professionals arrive. Civil engineers, structural engineers, geotechnical experts, surveyors, equipment operators, safety inspectors, concrete specialists, steel fabricators, electricians, environmental consultants, project managers. Every person has a clearly defined responsibility, yet all of them must work together as one coordinated team. Communication becomes just as important as technical expertise. Every morning begins with detailed safety briefings. Weather forecasts are reviewed. Equipment inspections are completed. Construction schedules are updated. Potential hazards are identified before work even starts. Because on projects of this scale, safety is never optional. It is the foundation upon which everything else depends. Then comes the moment everyone has been waiting for. The first excavator lowers its bucket into the ground. It may seem like a simple action, but it marks the beginning of a journey that will involve millions of work hours, thousands of deliveries, countless engineering decisions, and years of relentless effort. From this point forward, every day brings visible progress. Earth-moving machines reshape the landscape. Bulldozers level enormous areas with remarkable precision. Dump trucks transport thousands of tons of soil around the clock. GPS-guided equipment ensures every cut-and-fill operation follows engineering specifications within just a few centimeters. As excavation continues, the true scale of the project finally becomes visible. Gigantic foundation pits stretch across the site. Tower cranes begin arriving one by one. Temporary retaining walls secure deep excavations. Drainage systems redirect groundwater away from critical work zones. Concrete batching plants are installed nearby to ensure a continuous supply of fresh concrete. The once empty landscape rapidly evolves into a city of machines. Towering cranes dominate the skyline. Powerful excavators work side by side. Concrete pumps extend hundreds of feet into the air. Every movement follows a carefully synchronized plan. To an outside observer, the site may appear chaotic, but beneath the surface lies extraordinary organization. Every truck arrival, every crane lift, every concrete pour, every steel delivery is scheduled with remarkable precision. Because in mega-project construction, even a small delay can trigger a chain reaction affecting hundreds of workers and millions of dollars. This is only the beginning. Beneath the surface, engineers are preparing to build foundations capable of supporting some of the largest structures humanity has ever created. And that remarkable process begins next. Before a single column rises into the sky, before the first steel beam is lifted into place, and long before the finished structure captures the world's attention, there is one phase of construction that almost no one will ever see again: the foundation. Hidden beneath layers of concrete, steel, and earth, the foundation is the silent giant supporting everything above it. If it fails, the entire project is at risk, regardless of how impressive the final structure may appear. That is why engineers often spend more time building what lies underground than what people eventually see on the surface. The process begins with one critical question: can the ground safely support the enormous weight of the structure? The answer is rarely simple. Even within the same construction site, soil conditions can vary dramatically. One area may rest on dense rock, while another sits above soft clay or loose sand. Underground water, buried utilities, and even ancient riverbeds can introduce unexpected complications. To eliminate uncertainty, geotechnical engineers conduct extensive site investigations. Specialized drilling rigs extract core samples from deep beneath the surface, sometimes reaching depths of 50 meters or more. Every sample is carefully analyzed in laboratories to measure its strength, density, moisture content, and long-term stability. These results determine the type of foundation the project will require. For smaller buildings, shallow footings may be sufficient, but mega projects demand something far more powerful: deep foundations. One of the most common solutions is the bored pile. Using enormous rotary drilling machines, workers create perfectly vertical shafts deep into the ground. Some piles extend more than 70 meters below the surface, reaching solid bedrock capable of supporting thousands of tons. Once drilling is complete, a massive steel reinforcement cage is carefully lowered into the shaft. Then comes one of the most delicate operations in the entire process: concrete placement. Instead of pouring concrete directly from the surface, engineers often use tremie pipes that extend to the bottom of the pile. Fresh concrete flows upward from below, gradually replacing the drilling fluid while preventing contamination in air pockets. Every cubic meter is monitored. Every batch is tested. Because once the pile is complete, there is no practical way to inspect its interior with the naked eye. Advanced technology takes over. Ultrasonic testing, cross-hole sonic logging, thermal monitoring, and load testing verify that each pile meets strict engineering standards before construction continues. For the largest bridges and skyscrapers, thousands of these piles may be required. Together, they create an underground forest of reinforced concrete capable of supporting structures that weigh millions of tons. But deep foundations alone are not enough. Many projects must also overcome unstable ground. Soft soil can compress over time, causing dangerous settlement that may damage roads, railways, pipelines, or buildings. To solve this problem, engineers employ a range of ground improvement techniques. Vibrocompaction densifies loose sand by using powerful vibrating probes. Stone columns reinforce weak soils while improving drainage. Deep soil mixing combines cement with existing ground to create stronger load-bearing material. In some locations, giant surcharge embankments are built months before construction begins. Their enormous weight compresses the soil naturally, allowing most settlement to occur before the permanent structure is built. Patience becomes an engineering tool. Sometimes waiting 6 months today prevents decades of structural problems in the future. Groundwater presents another major challenge. Excavating below the water table can quickly flood an entire construction site. To keep the work area dry, dewatering systems operate continuously. Powerful pumps remove groundwater through networks of deep wells, while waterproof retaining walls isolate excavation zones from the surrounding soil. On coastal projects, engineers may even construct massive cofferdams, temporary watertight structures that create dry working environments in the middle of rivers, lakes, or oceans. Inside these protected areas, workers can safely excavate, install foundations, and pour concrete where water once flowed freely. Then comes the foundation slab itself. For megaprojects, this is no ordinary concrete pour. Some foundation slabs require tens of thousands of cubic meters of concrete delivered continuously over several days without interruption. Hundreds of concrete trucks arrive in carefully timed sequences. Tower cranes, concrete pumps, and quality control teams work around the clock. Temperature sensors embedded within the concrete monitor heat generated during curing. If internal temperatures become too high, thermal cracking could weaken the structure before it is ever used. Every detail matters. Every measurement is recorded. Every decision is based on data, because repairing a foundation after the building is complete is almost impossible. The only acceptable solution is getting it right the first time. As weeks pass, enormous excavation pits gradually disappear beneath layers of reinforced concrete. What once looked like an empty hole now becomes the strongest part of the entire project. Invisible to future visitors, forgotten by most people, yet carrying every floor, every bridge deck, every runway, and every tower for generations to come. With the underground work finally complete, attention can now shift upward. The next stage will transform engineering drawings into visible reality as thousands of tons of structural steel begin rising toward the sky, one precisely engineered component at a time. With the foundation finally complete, the project enters one of its most exciting and visually dramatic phases. For the first time, the structure begins to rise above the ground. What was once a vast construction pit slowly transforms into a recognizable building, bridge, or transportation hub. This is the stage where years of planning become visible to the world. But despite the impressive sight of cranes lifting enormous steel sections into the sky, very little is left to chance. Every structural component has already been designed, analyzed, tested, and assigned a precise location long before it reaches the construction site. Modern megaprojects rely heavily on prefabrication. Instead of manufacturing thousands of individual components in the middle of a busy construction site, steel beams, columns, bridge segments, and reinforced concrete elements are produced inside highly controlled factories. There, advanced robotic equipment cuts steel with remarkable precision. Automated welding systems create joints that meet strict international standards. Laser scanners inspect every finished component, ensuring dimensions remain accurate down to just a few millimeters. Only after passing multiple quality inspections are these massive elements transported to the project site. For some projects, logistics become almost as challenging as construction itself. Bridge sections weighing hundreds of tons travel hundreds of kilometers by truck, rail, or barge. Entire highways may be temporarily closed during the night to allow oversized cargo to pass safely. Police escorts coordinate traffic, while engineers monitor every movement. Sometimes transportation takes longer than the actual installation. Once the components arrive, another carefully choreographed operation begins. Tower cranes dominate the skyline. Some stand more than 200 meters tall. Others can lift loads exceeding 100 tons with astonishing accuracy. Every crane operator works closely with rigging crews positioned both on the ground and high above the site. Communication is constant. Wind speed is monitored continuously. Load calculations are verified multiple times. A sudden gust of wind or an improperly balanced load could create dangerous conditions within seconds. That is why safety procedures are followed with absolute discipline. No lift begins until every member of the team confirms that conditions are safe. As steel columns rise floor by floor, surveyors constantly measure their position using robotic total stations and GPS equipment. Even the slightest deviation is corrected immediately. A structural error of only a few millimeters at ground level could become several centimeters by the time the building reaches its full height. Precision today prevents expensive corrections tomorrow. For reinforced concrete structures, another remarkable process unfolds. Large formwork systems are assembled around steel reinforcement cages. Concrete pumps extend long articulated booms high into the air, delivering fresh concrete exactly where it is needed. Workers vibrate the concrete carefully to eliminate trapped air and ensure complete compaction around the reinforcement. Every pour follows a detailed sequence. Too much pressure inside the formwork could cause failure. Pouring too quickly might create structural defects. Even the outside temperature influences the curing process. During hot weather, concrete must often be cooled before placement. In colder climates, insulated blankets and heating systems protect freshly poured concrete from freezing. Nature never stops influencing construction. Engineers simply learn how to work with it. As the structure grows taller, temporary support systems become increasingly important. Massive scaffolding surrounds the building. Protective platforms shield workers below from falling objects. Temporary braces stabilize partially completed sections until the entire structural frame is fully connected. Every piece of temporary equipment plays a critical role, even though it will eventually disappear once construction is finished. One of the greatest advances in modern construction is the use of digital monitoring systems. Sensors installed throughout the structure measure movement, vibration, temperature, and stress in real time. Engineers can compare actual structural behavior with computer simulations every single day. If unexpected movement occurs, the system immediately generates an alert, allowing engineers to investigate before a small issue develops into a serious problem. Technology has transformed construction from reactive problem solving into proactive risk management. Yet despite all the advanced software, robotics, and automation, the most valuable resource on any construction site remains human experience. Experienced ironworkers guide enormous steel beams into place with incredible precision. Concrete specialists recognize subtle changes in material behavior. Crane operators develop an instinct for balance that no computer can fully replicate. Project managers coordinate thousands of individual activities while constantly adapting to changing conditions. Megaprojects are ultimately built by people. Machines provide strength. Technology provides accuracy. But it is skilled professionals who bring everything together. Week after week, the skyline changes. Steel skeletons become complete structural frames. Concrete cores climb steadily higher. Bridge spans stretch farther across rivers and valleys. What once existed only as digital models is now becoming a permanent landmark. However, constructing the main structure is only part of the challenge. The project must still survive the forces of nature. Powerful winds, earthquakes, floods, extreme temperatures, and decades of continuous use. In the next chapter, we'll discover how engineers design these incredible structures to withstand some of the harshest environments on Earth while keeping millions of people safe every single day. Completing a massive structure is only half the battle. The real challenge begins after construction is finished. Every bridge, tunnel, skyscraper, airport, and dam must withstand the relentless forces of nature not for a few years, but often for the next 50, 100, or even 200 years. Unlike ordinary buildings, megaprojects are designed with the expectation that they will face the unexpected. Powerful earthquakes, Category 5 hurricanes, typhoons carrying torrential rain, record-breaking heat, freezing winters, floods, landslides, and even gradual changes caused by climate change. Every one of these threats is considered long before construction begins. Engineers don't simply ask whether a structure can stand. They ask how it will behave when nature pushes it to its limits. For skyscrapers, wind is often a greater concern than weight. At extreme heights, even a moderate breeze can create noticeable movement. Strong winds generate invisible forces that cause towers to sway from side to side. Without proper engineering, occupants could feel uncomfortable long before the structure itself is in danger. To solve this challenge, designers carefully shape the exterior of the building to reduce wind resistance. Rounded corners, tapered profiles, open mechanical floors, and aerodynamic facades all help break up powerful wind currents before they can build dangerous pressure. Some of the tallest towers on Earth also contain enormous tuned mass dampers. These giant suspended weights, sometimes weighing hundreds of tons, move in the opposite direction of the building's motion. By counteracting vibration, they significantly reduce sway during storms and improve comfort for everyone inside. Earthquakes present an entirely different engineering challenge. When the ground suddenly shifts beneath a structure, enormous forces travel upward through the foundation. Instead of attempting to resist every movement, many modern buildings are designed to move safely with the earthquake. Flexible steel frames absorb energy rather than cracking under pressure. Special expansion joints allow different sections of a structure to move independently. Some buildings are even supported on base isolation systems. Massive rubber and steel bearings separate the building from the ground below, dramatically reducing the amount of seismic energy transmitted into the structure. During a major earthquake, the ground may move violently, while the building above experiences only a fraction of that motion. Bridges require equally sophisticated protection. Every day, bridge decks expand under the heat of the sun and contract again as temperatures fall at night. Over the course of a year, these movements can measure several centimeters or more. Without expansion joints and specially designed bearings, enormous internal stresses would gradually damage the structure. Engineers must also consider heavy traffic, strong crosswinds, ship impacts, and even the possibility of accidental collisions. Each scenario is carefully simulated using advanced computer models long before the bridge opens to the public. Water presents another constant challenge. Coastal bridges, offshore platforms, and marine structures remain exposed to salt water every day. Salt accelerates corrosion, gradually weakening unprotected steel over time. To combat this, engineers use specialized coatings, galvanized steel, stainless reinforcement, and high-performance concrete designed specifically for aggressive marine environments. Regular inspections ensure that even the smallest signs of deterioration are detected early. Modern infrastructure is no longer built with the expectation that it will simply survive. It is built to be monitored continuously throughout its entire lifespan. Hidden throughout many megaprojects are thousands of sensors. These devices measure vibration, temperature, humidity, structural movement, konkrete steel stress, and even microscopic cracks. Together, they form a digital nervous system, constantly reporting the health of the structure. Artificial intelligence analyzes this stream of information around the clock. If unusual behavior is detected, engineers receive immediate alerts, allowing maintenance crews to respond long before a visible problem develops. This approach, known as predictive maintenance, is transforming the future of infrastructure. Instead of waiting for damage to occur, engineers can prevent failures before they happen. At the same time, sustainability has become an essential part of modern engineering. Many new projects incorporate recycled construction materials, low-carbon concrete, renewable energy systems, rainwater collection, and intelligent energy management technologies. Some buildings even generate a significant portion of their own electricity through integrated solar panels and advanced facade systems. Engineering success is no longer measured only by size. It is measured by resilience, efficiency, safety, and the ability to serve future generations while minimizing environmental impact. As the final structural inspections approach, attention begins to shift toward the last stage of construction. The giant cranes that once dominated the skyline will soon disappear. Temporary scaffolding will come down. Interior systems will come to life. Roads, railways, lighting, communications, and smart technologies will all be connected into one fully functioning system. The project is entering its final transformation. And in the next chapter, we'll witness how years of planning, engineering, and construction come together to create a finished masterpiece ready to change the lives of millions. After years of planning, months of excavation, and countless hours of construction, the project finally reaches its most rewarding stage. The structure is standing. The skyline has changed. But surprisingly, the work is far from over. In fact, some of the most complex engineering activities begin only after the main structure has been completed. This is where a construction site slowly transforms into a fully operational piece of infrastructure capable of serving millions of people. Heavy machinery gradually disappears. Tower cranes that once dominated the skyline are dismantled section by section. Temporary access roads are removed. Construction fences begin to come down. For the first time, people can clearly see the true shape of the project. Inside the structure, thousands of specialists begin working simultaneously. Electricians install kilometers of power cables throughout the building. Mechanical engineers connect heating, ventilation, and air conditioning systems designed to operate efficiently under every weather condition. Plumbers complete extensive networks of water supply, drainage, and fire protection systems. Communication engineers integrate fiber optic networks, security systems, surveillance cameras, and intelligent building controls. Although these systems remain hidden behind walls and ceilings, they are just as essential as the steel and concrete supporting the structure itself. A modern megaproject is no longer simply a physical structure. It is an intelligent system. Thousands of sensors continuously monitor lighting, air quality, temperature, energy consumption, occupancy levels, and equipment performance. Building management software automatically adjusts these systems in real time, reducing operating costs while improving safety and comfort. Large transportation hubs operate in much the same way. Airports coordinate baggage handling, passenger movement, aircraft scheduling, and security screening through highly integrated digital platforms. Modern railway stations monitor train arrivals, passenger flow, platform safety, and maintenance activities around the clock. Smart bridges measure traffic loads, wind conditions, structural vibration, and weather changes every second. Data has become one of the most valuable construction materials of the 21st century. Attention then turns to the exterior. Glass curtain walls are carefully installed one panel at a time. Each panel must align perfectly with the surrounding facade while maintaining weather resistance and thermal efficiency. Workers suspended hundreds of meters above the ground perform this delicate task with extraordinary precision. At ground level, landscaping crews reshape the surrounding environment. Trees are planted, walkways are completed, road markings are painted, public spaces begin to emerge where construction equipment once operated. Lighting systems transform the project after sunset, highlighting architectural features while improving visibility and safety. Yet appearances alone are never enough. Before the project can open to the public, every critical system must undergo extensive testing. Elevators operate continuously for days. Emergency generators are activated under simulated power failures. Fire detection and suppression systems are tested repeatedly. Ventilation systems are measured to ensure proper airflow. Water supply networks are pressure tested. Electrical systems are subjected to full operational loads. For transportation infrastructure, the testing becomes even more demanding. Bridges may be loaded with dozens of fully loaded trucks, positioned in carefully calculated patterns to verify structural performance. Engineers monitor deflection, vibration, and stress using precision instruments capable of detecting movements smaller than a millimeter. Tunnel ventilation systems simulate emergency smoke conditions. Airport runways undergo friction testing to ensure aircraft can safely land under wet weather conditions. Every result is carefully documented. Every requirement must be satisfied before final approval is granted. Government inspectors, independent engineering consultants, safety authorities, and project owners all participate in the final evaluation. Only after every inspection has been successfully completed does the project receive permission to begin operation. Then comes the moment. Maybe everyone has worked toward for years. Construction barriers are removed. The gates open. The first vehicles cross the bridge. The first passengers enter the terminal. The first trains arrive at the station. The first employees move into the building. For the public, this may appear to be the beginning of the project story. But for the thousands of engineers, architects, construction workers, equipment operators, inspectors, and planners who dedicated years of their lives to making it possible, it represents the successful conclusion of an extraordinary journey. Yet even after opening day, the work is not truly finished. Maintenance teams immediately begin monitoring every critical system. Regular inspections continue throughout the life of the structure, because great engineering is never judged solely by how quickly it is built. It is judged by how safely, efficiently, and reliably it continues to serve people for decades to come. And in our final chapter, we'll look beyond today's achievements to explore how emerging technologies are shaping the future of construction, and why the next generation of megaprojects may be even more extraordinary than anything we've seen so far. Every generation leaves behind monuments that define its era. The pyramids demonstrated the ingenuity of ancient civilizations. Great castles and cathedrals reflected centuries of craftsmanship. Steel skyscrapers transformed modern cities. Today, a new generation of megaprojects is once again redefining what humanity can achieve. But the future of construction will not be measured only by taller buildings or longer bridges. It will be measured by intelligence, sustainability, resilience, and the ability to adapt to an ever-changing world. Artificial intelligence is already transforming how engineers design complex structures. Instead of spending weeks comparing thousands of design alternatives, advanced algorithms can evaluate countless possibilities within hours. AI helps identify more efficient structural layouts, reduce material waste, improve construction schedules, and even predict potential risks before work begins. At the same time, robotics is changing construction sites around the world. Autonomous surveying drones capture highly detailed aerial maps in minutes. Robotic equipment assists with repetitive welding, bricklaying, and concrete finishing. Some machines are now capable of operating with minimal human intervention, improving both productivity and worker safety. Digital twins represent another major breakthrough. These are not simply three-dimensional models. They are living digital replicas of real structures. Connected to thousands of sensors, digital twins continuously receive real-time information throughout the life of a building or bridge. Engineers can monitor structural performance, predict maintenance requirements, and evaluate future upgrades without interrupting normal operations. Construction itself is becoming more sustainable. New generations of low-carbon concrete significantly reduce greenhouse gas emissions. Recycled steel and environmentally responsible materials are becoming standard on many major projects. Solar energy, rainwater harvesting, smart ventilation systems, and energy-efficient facades are no longer optional features. They are rapidly becoming essential components of modern infrastructure. The cities of tomorrow will also become increasingly connected. Transportation networks, buildings, power systems, and communication infrastructure will operate together through intelligent digital platforms. Traffic congestion can be reduced automatically. Energy consumption optimized continuously. Maintenance scheduled before failures occur. Infrastructure will no longer simply respond to problems. It will anticipate them. Yet despite all of these remarkable technological advances, one thing remains unchanged. Behind every successful megaproject stands the dedication of thousands of people. Architects who imagine bold new possibilities. Engineers who transform ideas into practical solutions. Construction workers who perform demanding tasks with exceptional skill. Crane operators, surveyors, inspectors, project managers, and countless specialists working together toward a single goal. Technology provides extraordinary tools, but human creativity, experience, and determination continue to drive every great achievement. Every bridge that connects distant communities, every tunnel carved through solid mountains, every airport welcoming travelers from around the world, and every skyline transformed by modern engineering tells a story far greater than concrete and steel. It tells the story of human ambition, a story of solving problems once thought impossible, and a story that continues to evolve with every new project. The next generation of engineering challenges has already begun. Somewhere, a new foundation is being excavated. A new bridge is taking shape. A new skyline is rising. And once again, people are proving that with vision, innovation, and determination, almost nothing is impossible. Thank you for joining us on this journey through the world of mega construction. If you enjoy exploring extraordinary engineering, groundbreaking technology, and the incredible projects shaping our future, be sure to subscribe to Ant Hill's BuildVerse. We'll see you in the next adventure.